Hello, this is Tim Smith, the Academic Support Coordinator for St. John's River State College, St. Augustine campus. This lesson is part one of a series of 2 videos on functions of 2 or more variables and is designed as a study aid and supplement to the math tutoring services offered at St. John's River State College. In this video, we will discuss the definition of a function of 2 variables, the definition of a function of 3 variables, domain, the limit of a function of 2 variables, partial derivatives, and the slope of the tangent line. The area of a rectangle is a quantity based on both the length of the base and the height of the rectangle. A equals b times h. We can express this equation as a function of 2 variables. A equals f of bh, or equals b times h. Let D be a non-empty subset of the xy plane. A function f of 2 variables x and y is a relation that is associated with each points x and y of D, a unique number z equals f of xy. The volume of a rectangular solid is a quantity based on the length of the base, depth, and height of the solid. V equals b times d times h. We can express this equation as a function of 3 variables. V equals f of b dh, or equals b times d times h. Let D be a non-empty subset of the points in space. A function f of 3 variables x, y, and z is a relation that associates with each point x, y, and z of D, a unique number w equals f of x, y, z. For example, evaluate the following functions. Let f of xy equal 3x plus 2y plus xy. Find f of 2, 1. In this case, we replace all x's with 2 and all y's with 1. Simplify to get 6 plus 2 plus 2, which equals 10. In another example, let f of xyz equal 3xy plus z, all over x squared plus y squared plus z squared. Find f of 2, 1, 3. Again, we replace x's with 2, y's with 1, and z's with 3. Simplify to get 6 plus 3 all over 4 plus 1 plus 9, which equals 9 over 14. The domain of a multivariable function is found by evaluating each variable as it applies to the entire function. F of xy equals x over y. The domain is a set of x's and y's such that y is not equal to 0. In another example, f of xyz equals z times the square root of x times y. Since we know that a square root cannot be calculated on a negative number, it means that x times y must be greater than or equal to 0. Therefore, the domain of the function is a set of all x, y's, and z's such that y is greater than or equal to 0 and x is greater than or equal to 0, or y is less than or equal to 0 and x is less than or equal to 0. For example, find the limit of the following multivariable function. The limit as xy approaches 2, 1 of x squared plus x times y minus 6y squared all over x squared plus 4y squared. This limit may be solved by substitution. So 2 squared plus 2 times 1 minus 6 times 1 squared all over 2 squared plus 4 times 1 squared. This simplifies to 4 plus 2 minus 6 all over 4 plus 4, or 0 over 8, which equals 0. The limit as xy approaches 0, 0 of e to the x minus 4 over e to the y. Using substitution, we get e to the 0 minus 4 over e to the 0. This simplifies to 1 minus 4 over 1, or negative 3. Let z equal f of xy be a function of 2 variables, and let xy be any interior point of the domain of f. The first order partial derivative of f with respect to x, and the first order partial derivative of f with respect to y, are the functions f using the subscript x and f using the subscript y, and are defined as follows. The partial derivative of f of xy with respect to x equals the limit as delta x approaches 0 of f of x plus delta x y minus f of x y over delta x. This partial derivative treats y as a constant. The partial derivative of f of xy with respect to y equals the limit as delta y approaches 0 of f of xy plus delta y minus f of xy over delta y. This partial derivative treats x as a constant. Partial derivatives may also use Leibniz notation. The partial derivative of f of xy with respect to x equals df dx, which equals dz dx, using the script d for the partial derivative. Also, the partial derivative of f of xy with respect to y equals df dy equals dz dy, also using the script d. As an example, find the partial derivative of f of xy with respect to x and the partial derivative of f of xy with respect to y for each of the following functions. F of xy equals x times y squared plus sine x. To find the partial derivative with respect to x, we assume y is a constant and to take the derivative of the x portions of each term. Therefore, the partial derivative is y squared plus cosine x. To find the partial derivative with respect to y, we treat x as a constant and take the derivative of the y components of each term. The partial derivative with respect to y is 2xy. In another example, find the partial derivative of the following function at a point. We start with the function f of xy equals sine x plus x cosine y. Then we find the partial derivative of f with respect to x at pi over 3 pi over 4. Then the partial derivative of f with respect to y at pi over 3 pi over 4. For the partial derivative of f with respect to x, we treat the cosine y term as a constant, which means the partial derivative equals cosine x plus cosine y. This function at pi over 3 pi over 4 equals cosine pi over 3 plus cosine pi over 4. Cosine pi over 3 equals 1/2, and cosine pi over 4 equals the square root of 2 over 2. This simplifies to 1 plus the square root of 2 over 2. For the partial derivative of f with respect to y, we treat x terms as constants. So the partial derivative of cosine x with respect to y equals 0. Then the partial derivative of x cosine y equals negative x sine y. This function at pi over 3 pi over 4 equals negative pi over 3 times the square root of 2 over 2. This simplifies to negative pi times the square root of 2 over 6. If z equals f of xy is a function of two variables, and the partial derivative of f with respect to x, where the variable y is fixed at y equals y sub 0, and the partial derivative of f with respect to y, where the variable x is fixed at x equals x sub 0, both exist, then the following is true. Given a function in two variables, z equals f of xy, that creates a curve in three-dimensional space, if we take the plane y equals y sub 0 so that it intersects the surface at the curve z equals f of xy, then choose a point on the curve x sub 0, y sub 0, z sub 0. The partial derivative of f of x sub 0, y sub 0 with respect to x equals the slope of the tangent line to that given point. Given a function in two variables z equals f of xy that creates a curve in three-dimensional space, if we take the plane x equals x sub 0 so that it intersects the surface at the curve z equals f of xy, then choose a point on the curve x sub 0, y sub 0, z sub 0, the partial derivative of f of x sub 0, y sub 0 with respect to y equals the slope of the tangent line to that given point. For example, find the equation of the tangent line to the curve of intersection for the following plane at the indicated points. Z equals x squared plus y squared and y equals 2 at the point 1, 2, 5. F of xy equals x squared plus y squared. The partial derivative of f with respect to x equals 2x. The partial derivative of f at y equals 2 is also 2x. At the point 1, 2, 5, the slope of the tangent line is 2 and lies on the plane y equals 2. Use the slope-intercept form. Z minus z sub 0 equals the slope m times x minus x sub 0. Fill in the values from the point for x sub 0 and z sub 0 to get z equals 2x plus 7. If you have further questions on this or any other math topic, or wish in-person tutoring, please consult the Academic Support Coordinator on your respective campus. Thank you and good luck with your studies.